Today we're testing the harmonic measurement ability of the bolt, and it's also a test of the analog front end. Testing any nonlinearities in the front end and the frequency response and flatness of the front end for both voltage and current in the bolt. So we have a three-phase power supply that can supply programmable harmonic pattern. For voltage, we have a resistive load for current, and we have a bolt connected with all channels tied together for voltage, using TLR CTs for the current, and a 10 amp resistive shunt in series with this resistive load space heater to give us a current measurement that we can run into the spectrum analyzer. We have voltage on the top plot, current on the bottom plot, with a 20-to-1 probe for voltage, and we're measuring on a shunt that is designed for 10 amps full scale with 100 millivolt output at that current, and also looking at the voltage and current waveforms here on the scope, so we can make sure that we're generating what we think it generate, and make sure the bolt agrees with the spectrum analyzer. And we're using the PMIView app on an iPad connected to Wi-Fi. So the first test is a 60 Hz sine wave. This should be as a clean sine wave, should have no harmonic content at all. So in theory, the THD should be 0 for voltage and for current. We can see it looks like a clean sine wave on the scope. Let's take a look at the harmonic meter readings. We can see we're at 0.1% distortion for voltage and for current. That's really the limit of the power supply. That's a very low distortion, very difficult to get below that with a large power supply. We can see on the spectrum analyzer, we have 60 Hz fundamental. Let's put a marker on 60 Hz for voltage. We have 5.02 volts RMS as read by this 20X probe, which corresponds to 100 volts on the bolt input, and that's what we see. We have 99.9, 100, 100 for the 3 voltage channels. And with this size resistive load, we have 6.07 to 6.0 amps, 6.08 amps on current. And the harmonics are all 0. And with the THD of 0.1%, very low distortion here at the limits of the power supply itself. So with our next test, we're going to test the flatness of the passband for the bolt to make sure that each harmonic, all the way up to the 51st harmonic, is the correct level. We have a special pattern where every 5th harmonic we have a line. These show exactly 5 volts in amplitude for voltage and the proportional amplitude for current. And you can see on the spectrum analyzer all the way up to 3 kilohertz. These are flat, and this is the special waveform that does this. Let's check the harmonic levels on the bolt. Harmonic meter display, we can see 100 volts on the first harmonic, 5 volts for the 5th harmonic, and then the next one we have the 11th harmonic, and so forth up the spectrum, all 5 volts and proportional here for current. Let's corroborate that with the spectrum analyzer. We have the marker at 300 Hertz, the 5th harmonic, and we're reading 250 millivolts, which times 20 is 5 volts. And you can see these are all the same level. We can look at the harmonics on the bar chart. So here we have voltage. Again, we have a line on periodic harmonics all the way up, and we can just pick any one up. Pick any one here, the 35th harmonic, for example. Here we're at 5.0 volts, 4.9 volts. Here we see that's flat across the passband. Analog front end of the bolt is flat all the way up to 3 kilohertz, as we see with the special waveform. Now another test is the two-tone test. This is a test of linearity of the bolt front end. With a two-tone test, you put 2 sine waves at different frequencies, and you check for the sum and difference frequencies. Any nonlinearity will manifest itself as mixing in the frequency domain. So here we have 100 volts at the first harmonic, we have 20 volts at the 7th harmonic, and we see the same thing on the spectrum analyzer. Let's turn off the fundamental to make sure there are no other frequencies present. So the two-tone test will produce other frequencies, sums and differences of 60 Hertz to 420 Hertz that would manifest themselves here as other harmonics. But we see these levels are all close to 0. We can look at the meter display to verify that. We have 100 volts at the first harmonic, we have 20 volts at the 7th harmonic, and all the other harmonics are 0 for voltage and for current, showing that it's a very linear front end. There's no mixing going on, nonlinearities in the bolt. So with this test, we have 2 closely spaced harmonics, and the test is to make sure that the harmonic in between is close to 0 or absolutely 0, to make sure there's no leakage from one frequency bin to an adjacent bin. We can see the waveform here in the scope. We have, of course, 60 Hertz at 100 volts again, and we have 2 closely spaced harmonics here. We have the 5th and 7th harmonic, the test is to make sure that it's 0 in between, that there's no leakage from 2 high harmonics to one that's 0 in between. We can see these are 30 volts, proportionally sized currents, and in between we have basically 0. Look at the meter reading to corroborate. 30, 29.9, and the 6th harmonic is exactly 0 for voltage and for current. So we passed the two-tone test, or the spectral leakage test. There is no leakage from high harmonics to an adjacent harmonic. The adjacent harmonic still reads 0, and we can see that on the spectral analyzer as well. Now for our next test, we are going to test the ability to resolve a very small harmonic, especially one next to a large harmonic. And with this pattern, we have a very large 7th harmonic and a very small 9th harmonic. We want to make sure the 9th harmonic is being measured correctly, even in the presence of a nearby large harmonic. So in the waveform and the scope, we can see it's mostly 60 Hz in 7th harmonic. The 9th harmonic is going to be impossible to see in the time domain. So we can see 60 Hz, we can see the 7th harmonic is large, the 9th harmonic is very small here. Let's take a measurement, 540 Hz. We have roughly 10 millivolts times 20, that corresponds to 0.2 volts. And here on the meter screen, we see we're 100 volts at the 1st harmonic. We see 19.9 to 20 volts at the 7th harmonic, and the 9th harmonic is 0.2 volts. So even in the presence of other large harmonics, we still have good resolution down to very small levels for voltage, and for current we see the same thing. Proportionally here in the 6th or the 7th harmonic we have 1.2 amps, and then on the 9th harmonic we have 0.01 amps, which is the correct value given that it's 6 amps on the fundamental. And we can also check the THD as a sanity check. Should be 20% THD roughly. So we've stress tested the volt front end to test harmonic measurements. We've tested the harmonics up to the 50th harmonic to make sure that the volt front end is flat all the way up in frequency. We've also done some linearity tests, the two-tone test, the spectral leakage test, and the small harmonic adjacent to a very large harmonic to make sure there are no non-linearities in the analog section of the bolt, and also in the digital section of for the computations for the bolt. So the bolt harmonic measurements pass all the tests, and very good performance.